Displacement of water. When gases are collected by displacement of water, water vapor is present in the gas that's collected. So let's look at this as an example. Let's say we have potassium chlorate in a test tube, and we add some manganese dioxide, which is a catalyst, and we heat it up. The potassium chlorate will decompose into potassium chloride and oxygen gas. Potassium chloride is a solid, so it would stay in the test tube, but the oxygen gas would flow through the test tube, displace the water in this inverted bottle. The water would go out into the bucket, and then once all the potassium chlorate has been decomposed, the amount of oxygen gas collected can be measured. But the issue is that when we measure or collect a gas by displacement of water, not only is there oxygen gas in that bubble, but there's also some water vapor. And the water vapor pressure in that bubble is dependent on the temperature of the water. The warmer the water is, the more water vapor will be present. The cooler the water is, the less water vapor will be present. So we have a problem. We're going to take potassium chlorate, heat it up, and decompose it into potassium chloride and oxygen gas. And we're told that the oxygen gas was collected by displacement of water at 22 degrees Celsius for a total pressure of 754 torr. And when it says total pressure, that means that's the pressure exerted by the oxygen gas and the little bit of water vapor that's in that bubble. The volume of gas collected is measured, and it's 0.650 liters. It tells you that the water vapor pressure for water at 22 degrees Celsius is 21 torr. Now, it has to give you a temperature because water vapor pressure is temperature dependent. And you could actually look that value up on a table. It says calculate the partial pressure of oxygen gas, and then the mass of potassium chlorate originally decomposed. All right, so let's solve this problem. Our first step, we're going to write out our equation. So we've got potassium chlorate decomposing into potassium chloride and oxygen gas. And it tells us that when that oxygen gas is collected by displacement of water, the temperature is 22 degrees Celsius. The total pressure is 754 torr, and the volume of that bubble is 0.650 liters. And it tells us that the water vapor pressure is 21 torr. Well, the first part of the question is actually really easy. We want to find the partial pressure of the oxygen gas. Well, the total pressure equals the partial pressure of the water vapor plus the partial pressure of the oxygen gas. It gives us the total pressure, 754 torr. It gives us the water vapor pressure, 21 torr. So we can pretty easily calculate the partial pressure of the oxygen gas all by itself. And we would just subtract 21 from both sides of the equation. So our partial pressure of the oxygen gas is 733 torr. Now for the oxygen gas, we have a pressure, a temperature, and a volume. We can calculate how much gas we have. So PV equals nRT. The pressure exerted just by the oxygen gas is 733 torr. The volume is 0.650 liters. We want to solve for how much gas. We're going to use the R value that corresponds with torr, so 62.4 torr liter per mole Kelvin. And then our temperature is 22 degrees Celsius. We'll add 273 to that, and that'll give us 295 Kelvin. We can find out how many moles of oxygen gas we have. So we have 0.026 moles of oxygen gas. Now, we can do a stoichiometry problem. If we have moles of oxygen gas, we can figure out moles of potassium chlorate. And if we know moles of potassium chlorate, we can find out the grams of potassium chlorate. So if we produced 0.026 moles of oxygen, our balanced equation tells us that we produce 3 moles of oxygen for every 2 moles of potassium chlorate that decomposes. And then for every 1 mole of potassium chlorate, we've got 122.55 grams. So we get 2.1 grams of potassium chlorate. So that means that in order for us to have collected this amount of oxygen gas, we originally must have started with 2.1 grams of potassium chlorate.